Okay, so let's start the class. So so the test number 2 will be March 7. It's the first day and it's gonna be after the break. Ideally, it should be Tuesday, but I know some of you have jobs or they go on vacation, whatever. But don't erase your memory. So for test 2, it's gonna be electrostatics, right? So it's going to be voltage, electric field, and capacitors. So we're talking about unit 2. Okay? Yes. There are going to be conceptual questions and some numerical questions. I have posted a practice test and it does not count. Okay, so it doesn't count in the final grade, but I recommend to do it. There is also homework due coming up. If you need an extension, let me know, but it will be great if you do it before test 2, so you can review for the test. Okay, so it's as usual, make sure you print out your equation sheet, make sure you bring a pen, calculator, it's in person, on paper. And make sure you sign up on the screen. Okay, so first thing, I want to make sure that you know how to use your equation sheet, right? So before a test, always go over the equations that are available here. So anything that you don't find, so then you know that you have to memorize it. So if we look through it together, so it's a nice review for the test. You see here that will be the electric force between two charges. So that equation is telling you something. Okay, you can uncover what it's telling you. It's telling you that the electric force between two charges is proportional to the product of the charges. So if you multiply one charge by 4, the force will be multiplied by 4, but it's also inversely proportional to the distance squared, which means if the distance between the charges is divided by 3, so the force will be multiplied by 9. So it's a typical conceptual equation. It's called the inverse square law. Here, that equation here tells you that the electric field is a vector, so it has a magnitude, but also a direction. So for example, if you have a positive charge, the electric field will go outward. Typical question, again, conceptual question. If you have a negative charge, the electric field will go inward. So electric field is a vector. It has a magnitude. So the magnitude of the electric field is the force per unit coulomb. Okay, so if you have 1 coulomb of charge placed in an electric field, it will be acted upon by a force, right? So I'm reviewing also for the test. So the electric field is a force. So to find its magnitude, all you have to do is to substitute one of the charge by 1 coulomb. Okay, because it's a force acting on 1 coulomb of charge. That means that, say, Q1 is 1. So you have this equation. Hello, TP2000, you listen? So that will be the magnitude of the electric field, right? The electric field is inversely proportional to the distance squared. And then we talked about voltage. Remember, voltage is a property of 2 points. That will be the energy per coulomb, the energy per unit charge. Okay, so you can find the electrostatic potential energy. So the potential energy will be Q times delta V. Okay, because delta V is the energy, okay, per unit charge. So have Q as a charge, you multiply by Q. Is that clear? And then we learn about voltage. Okay, so that will be the equation for voltage for a point charge. That voltage is relative to very far away. So we take the voltage to be 0 very far away. So very far away could be the ground. Okay, so that will be the voltage, okay, because of a point charge. So it's the voltage produced by a point charge, and as you move away, if it's positive, the voltage goes down, and we talked about equipotential. Now, if you have a parallel plate capacitor, for example, we have seen that the electric field is uniform, and you see that the electric field will be the slope, delta V, okay? So the voltage across the plates divided by the distance between the plates. So it gives us a new unit for the electric field. So delta V, what's the unit for delta V? It's going to be the volt. Distance, the unit is in meter. So you have volt per meter, okay? So you can think of the electric field as a force per unit coulomb, or you can see the electric field as a slope. Okay, and then we talked about capacitor, okay, or we're going to talk about capacitor. You see that capacitor, it has a voltage across the plate. So you see the voltage equals Q over C, but everything here we're gonna do that today. But make sure you get used to this equation sheet and you know how to use it. Okay? So let's go back to here. So I talk about that a lot, and I use this app, okay, that you have access to. It's very nice to understand how they work. I don't know where we stopped. Did we start here? Hmm? Got there. Okay, so I just introduced it. So what is a capacitor? Okay, it's a device that can store charges. So for example, not for example, for a capacitor, you always have two conductors, like a defibrillator. One conductor will be positively charged and one conductor will be negatively charged. So it's like the configuration of the electric field is the electric field of a dipole. This electric field here wants to bring them together. Okay? Now you're gonna have energy stored inside your capacitor, like you have energy stored inside a defibrillator, right? And you can discharge that capacitor, so you can burp out all that energy stored through your heart, and the heart is going to contract because it's a muscle, and hopefully you can resuscitate someone. Okay, you have also an equation here for if you go back to my equation, where is my equation sheet here? You see here that will be the energy stored inside the capacitor. Capacitor being a parallel plate capacitor. Okay, so you have the equation here. Ah, okay. Is that in here also? Yes, I thought you are doing some piece of art. Definitely. So capacitors are used a lot in technology. So for example, in 1930s, the high-speed photography was developed, okay? And that was done at MIT. And the idea is that you take a very, very large capacitor and you discharge it in a plasma tube. So it means you're going to have a huge amount of current discharge in a small amount of time that will and then you will get a flash. If you want to do a demo, they are very easy demo. Let me get that paper. Okay, disappear. Okay, so that's what capacitors look like if you are doing some electric work. You see all those capacitors here? Now, we're going to define a new physical quantity, and we call that quantity the capacitance. Capacitance reminds you of capacity, that means volume, right? So you can say that small beaker has less capacity than this large beaker. So for a capacitor, it's going to work the same way. So the capacitance, okay, is going to be, by definition, the amount of charge per unit volt. So you take a capacitor here, okay, you apply 1 volt, how many coulombs it can hold. Okay, so that will be the capacitance. So if I go back to my app here, I can, you see, for a given voltage, can I put a voltage of 1 volt? Uh, So here you have the capacitance, and here you have the charge, and the voltage is 1.5. So let's change the voltage to about 1 volt. About 1 volt. And you see the capacitance, it's going to be about 0.9 times 10 to the negative 13. And so is the plate. You see? Now for the plate, I'm going to have 0.9 times 10 to the negative 13 coulomb. So what's the definition of the capacitance? It's going to be the coulombs, how many coulombs, how many charges you can store in a capacitor for a voltage equals to 1. So if you have 1 volt voltage, you see the capacitance will be equals to the charge. So capacitance only depends on the geometry of your capacitor. You can change the capacitance by increasing the plate area or by changing the distance between the plates. So what's going to happen if I increase the area? We have seen that. Increase the area, you are increasing the space, right, for the charge to go. So what's going to happen to the charge? Increase. So the capacitance is going to increase as well because you are changing the geometry. So I increase the area. Yeah, let's increase the area. You see, the capacitance goes up. If I decrease the area, the capacitance goes down. Likewise, I can change the distance between the plates. So I can decrease the plate. You're going to have larger capacitance and you can store more charge. If I increase the plate here, you're going to have less charge, less capacitance. So capacitance only depends on the geometry, and by definition, the capacitance will be the amount of coulombs per unit volt. Because it should be coulomb per volt, and the unit is called farad. So farad is named after Michael Faraday. Okay, so if I don't know where I am now. Okay, so if you go here, you see you have the definition here. Capacitance is charge per unit volt. Okay, so make sure you know how to use your equation sheet. Okay? Now you have this equation. So this is your parallel plate capacitor. In between them, you have an insulator. We call that a dielectric. Okay? Then you apply a voltage. And depending on the geometry, okay, you're going to get a lot of charge or not that much, right? And you have this equation. So for example, let's do a very simple application. So if you have 4 capacitor of 4 picofarad, that will mean 4 picocoulomb. Okay, pico means 10 to the negative 12 per volt. So can you find the charge? Three 3.6 times 10 to the negative 11. Did you all find that? Okay, so capacitance is by definition the number of charge in coulomb per unit volt. Okay, so you see here that will be your capacitance because you have the unit farad. So capacitance equals 4 pico. You look at your equation sheet. Pico means 10 to the negative 12. Okay, farad. You see, this is a volt here, so that will be your delta V. It's your voltage. Okay, so you plug in it. 4 times 10 to the negative 12 equals Q over, and delta V is 9. So you cross multiply. So Q is indeed 3.6 times 10 to the negative 11 coulomb. If I want in pico, okay, so that means I want to divide by 10 here, so you multiply by 10 there, or you divide by 10 to the negative 12, and you get 36 pico coulomb. So from here to there, you divide by 10 to the negative 12, okay, because 10 to the negative 12 coulomb is 1 pico coulomb. Look at your equation sheet. Okay, is that clear? You cross multiply, divide, yes? Okay. I have a, no, I want to convert that to pico. 1 pico is 10 to the negative 12. So I divide by 10 to the negative 12 to see how many picos goes into, right? 1 pico is 10 to the negative 12. So if you have 3.6 times 10 to the negative 11, how many pico? So you divide because you want to know how many picos goes into that. If you do it in your head, you see to get to 10 to negative 12, you divide by 10, so you have to multiply by 10 here. But you don't have to do it this way. Is that clear? Okay, so I just have a short movie, and make sure that during spring break you don't erase
Battery
anything
has the
in your
potential
head.
to create an electric field.
When a battery is connected between two pieces of metal, it forces charge to flow from one to the other until the potential difference between them is equal to the voltage of the battery.
Do you see you get a dipole? Do you see the electric field between the plus and the minus? Okay, like the water molecule. Water molecule is a dipole.
That creates an electric field between them. If the voltage is doubled, so is the charge.
So for the same capacitance, the charge that you can store inside the capacitor, okay, is proportional to the voltage you apply to for the same capacitance, so for the same geometry.
So is the potential difference. And so is the electric field. In general, the charge transferred is proportional to the voltage applied, and the constant of proportionality, C, is called the capacitance.
The Leyden jar was the first primitive electric capacitor.
Any two pieces of metal can form a capacitor. The shape doesn't matter. The two pieces of metal can be the plates of a parallel plate capacitor, or...
So this is a parallel plate capacitor, okay? So it has a specific geometry. So to change the capacitance, you can either change the area of the plates or the distance between them.
They can be the inner and outer parts of a Leyden jar.
The electric field in a parallel plate capacitor is really due to sheets of opposite charge facing each other on the metal surfaces. The field between the sheets is constant. The two sheets of opposite charge attract each other.
So remember, between those two plates, the electric field is constant, right? It's uniform. And when you connect that to a power supply, you are transferring energy from the power supply to the capacitor. So work is done by the battery on the capacitor, and that energy will be stored inside the electric field.
And hold each other in place. That's why a capacitor is such a useful device. If the voltage is held constant by a battery, the charge, and therefore the capacitance.
See, the capacitance, okay, depends only on the geometry.
Changes inversely as the distance between the plates and is proportional to the area of the plates.
So when you change the geometry, you see more charges are able to flow from the power supply to the capacitor. And you remember the story about the Leyden jar? And at the beginning, they connect all those capacitors together in a parallel setup. So they were able to increase the charge and then they could have a huge discharge. Okay, that was the first class when I went over history. Okay, so capacitance unit is the farad. Okay, so by the way, even when you have a Van Graaff generator, okay, let's say this is positively charged, so it's holding charge, right? Do you agree with that? You can hold it for a long time if the atmosphere is very dry. Can I call that a capacitor? Yes. Where is the minus? Where is the minus? Minus is very far away. It will be the ground. So you have a capacitor, okay? What are the two conductors? You have that spherical conductor, so Van Graaff generator, so that sphere, okay? And the minus will be the ground, will be far away. So you do store energy into the electric field, but you see, we've seen that last class on Tuesday. Because of that geometry, you are not able to store a lot of charges. So it means the capacitance will be very small, okay, because it's spherical. So that's why it's not dangerous. Okay, if you bring another here spherical sphere, you do have a capacitor, so that will be plus, that will be minus, and you can even have a discharge if the electric field is too strong. Is that clear? I emphasize electrostatics and electric field because in biology it's everywhere, and medicine as well, biotechnology also. So here you can have different geometry. So here that will be a huge one, okay, just for demonstration. Here, even this one, okay, it's also a capacitor because it can hold charge, but not that much. Remember, it's called an electroscope. Okay, so a parallel plate capacitor, that will be a parallel plate capacitor. Okay, you have an electric field between the plate. Okay, and it makes sense. How do you think, how do you write a capacitance? It depends on what? What did we say? So the capacitance only depends on the geometry, right? It means it's like a bucket or a beaker, you know, how much you can have, you can store, you can hold, right? So it depends on what? The surface area, 1, and then the distance. Very good. And you see how an equation can uncover the physics behind it. Okay, so even when you have a chemistry class or whatever, and you are dealing with equations, try to translate them. So you see, capacitance is proportional to the area, inversely proportional to the distance. So if you decrease the distance, it's like you increase the motivation. Okay, they say, oh, it's almost there, you know. So electric field will be stronger and the capacitance will be stronger if you decrease the distance. And then you have a constant here, okay, just to tune the equation right. Okay, so it's a way to tune. And this is called the permittivity of free space. And it's 8.85 times 10 to the negative 12. Okay, so let's do a simple one here. Okay, let's do a simple one. So all that is very easy. The only challenge is scientific notation. Okay, so make sure is to be able to use your TI. That's the only challenge here. And how to convert. That's all there is. So capacitance equals, here you have a constant, 8.85 times 10 to the negative 12 times the area over the distance. So you see, you translate here. What is the capacitance? So C question mark, blah, 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 blah. 1 meter square. When you see a distance square, that means it's area. Here, you see, it's just a distance. Okay, so I'm going to do D equals 10 to the negative 3 meters. Okay, and they say how much charge Q. So we have two equations to use here, right? 8.85 times 10 to the negative 12. So let's find the capacitance. Okay, I should put first question. Okay, they ask me, what is the capacitance? So just to make sure you know how to use your TI. With your TI, you just put parentheses. 1, and then here open the parentheses, and that will be 10 to the negative 3. Yeah, right. Negative 9. What's the unit? What's the unit? Farad. Oh, Farad. I don't know how. I know I had a name, someone named Fahad. So Farad, I don't know how to say it. So anyway, when you divide by 1000, you see, you move it up and it becomes plus 3. Okay, did you all get that? Right? So 1 millimeter. Make sure you know how to use your equation sheet, right? 1 millimeter is 10 to the negative 3 meter. One meter is 1,000 millimeters. Okay, do you all agree? Okay, B. Okay, do we have an equation with the delta V? That's okay, the way I remember. C equals Q over V. Or Q equals CV. Okay, you can say Q equals CV. Curriculum vitae. Q equals CV. So Q equals CV. Bless you. So 8.85 times 10 to the negative 9. and V is 10 to the 3. Do you agree? Okay. Oh, by the way, that's going to be called 8.85 nanofarad. Because if you buy capacitors, it's going to be written the maximum voltage you can apply and the capacitance. And you never use scientific notation, so they always use nanofarad, microfarad, millifarad, and so forth and so on. So what you get? Negative 5? Negative 5. Can you convert that to micro? Micro. 1 micro is 10 to the negative 6. So you divide by 10 to negative 6 to get micro. No, micro. Micro is 10 to the negative 6. Nano is 10 to the negative 9. So what did you say? Oh, yeah, you're right. 27, about 26.66 micro. You're right. Coulomb. Okay? Yeah. The C is what? Farad. It's named after Faraday. Q is Coulomb. C equals Q over V. So this is Farad, this is Coulomb, and this is volt. Coulomb per volt is Farad. I had a friend had Farad, but actually you should not say that. It's Farad. Faraday, named after Faraday. Okay? So, of course, parallel plate capacitor will take too much space. You cannot shove that in an integrated circuit. So there is a trick. You roll them up. Okay, so you take your two conductors. Okay, it works if you want to do like a demo with two pieces of aluminum. In between them, you need an insulator. Okay, and you roll them up and you shove that in a cylinder and that becomes a capacitor. So for example, I have another picture to show you the idea. So you cannot use that because of course it will be too hard to shove into an electronic circuit. So you put a layer of insulator between the two conductive plates and you roll them up. So that way you can have a huge area and you can have a huge capacitance. Is that clear? But it's still, all those capacitors that you see, it's still a parallel plate capacitor. Okay? So just to review the equation we have with parallel plate capacitor, you see, one plate is positively charged, one plate is negatively charged, and here you can visualize, what are we visualizing? Visualizing the electric field. Very good, okay? Remember they use castor oil, and then you can put little seed in between that get twisted, aligned with the electric field. Okay, they get polarized, and you can visualize it. And remember, we have this equation for a parallel plate capacitor. The electric field in between is constant, and it's going to be equals to the voltage between the plates divided by the distance between them, which is very much like the slope. Okay, so if you go back to the equation, you see, yeah, you have this equation here. Okay, and then you have this equation there for the capacitance I'm going to go back to what's that K here, but you see it's proportional to the area, inversely proportional to the distance. Okay? Are you with me? Everyone? And someone asked a question last class. You see, you have a parallel plate capacitor. So you can think of one plate, the minus one will be the 0. So this one will have a voltage of 12 volt, which means if you have 1 coulomb of charge here close to the positive plate, it will have an energy of 12 joule. Very good. So it's like potential energy. And then if you let go, all the potential energy is going to go into kinetic energy. Okay, so remember that's the idea of an X-ray machine. You accelerate the electrons and then they crash into a heavy metal, and all that kinetic energy that comes from the voltage, okay, turn into X-ray. So you have of course you need to have a huge voltage for that. Okay, now there is a way to enhance the capacitance. So if we use air, okay, we can use air between the plates like this. So here you have air and you have a capacitance here, right? Now, do you remember the story with the elephant fish? I talk about that a lot. But you see, if you have an insulator like air, but now I put something else, which is called a dielectric. So it's a non-conducting material, and you show that in between the plates. What's happening? What's happening to the charges? Do they stay the same on the plate or do they increase? Increase. Okay? Can you see what's happening inside that dielectric? It gets polarized. Very good. So the electrons cannot flow because it's an insulator. They can be pushed a little bit. So all those molecules here, they get polarized. So now you have minus here on the top. So that motivates plus charges to flow even more because they see the minus. Woo, minuses. Okay, let's go, right? So you're going to increase the amount of charge that you can store. Okay? So what's going to happen to the capacitance? Increasing. By having a dielectric between the plates, you can increase the capacitance. And if I ask you conceptual question, can an electric field go through a non-conducting body? The answer is yes. Okay? Can it go through a conducting body? The answer is no. So if it's not, do you remember the fish? So it can go through, an electric field can go through a body that is not conducting like this, you see, going through. But if it's conducting, no. You see, now you have another electric field. You see, you have another electric field from plus to minus. So it will make the electric field, the total electric field weaker. Okay, but I already talked about that fish a lot. Yes. Yeah, so it depends on the dielectric. Okay, so some dielectric are more efficient than others, and yes, so you increase the capacitance. So we have a list. I don't know if okay, to answer your question. So for example, you have the same equation. Capacitance is area divided by the distance. But now if you shove, for example, Teflon, if you shove Teflon, you see here, this is called the dielectric constant. Here has no unit. Now your capacitance is going to be multiplied by 2. So just by shoving dielectric between the plates, you enhance the capacitance. And it's always done this way because otherwise, how can you hold it up? Okay, you don't want those two plates to touch each other, otherwise the capacitor is going to discharge. So you always have a layer of non-conducting material, right? No, so if you have another like neoprene, prene, I don't know how to say it, but you see, it's multiplied by 7 almost. So in the old time, dielectric was made of paper, okay? So we call that, if you can still find them, like an antique, a fossil, let's say old capacitor, you had a paper between the plates. Is that clear? So when you are using a dielectric, you are using the same equation, except you multiply by the constant here. So it's a lowercase k or kappa, it's a Greek letter. Okay, and if I go back to the equations here, let's see. See here, the capacitance equals kappa, which is the dielectric constant, so it depends what you put between the plates, times the area divided by the distance, and it's going to be proportional to. Okay, is that clear? I'm lost. No, I'm not lost. So you see dielectric here, inside is going to be polarized, so you are able to attract more charges on the plate. Okay? Mica is 7. So they are more expensive capacitor and usually they are very small. So let's do an easy application, just maybe the first one. At least lay out the equation. Are you doing it? So you see the keyboard, you have a key, okay, let's say B. Let's select the key B. And you see it's attached to a capacitor. When you hit the key, when you push the key, you decrease the distance here. So by decreasing the distance, what's going to happen to the capacitance? Is it going to increase or decrease? Increase. So because you increase the capacitance, there is more room for more charges, right? So you have a current that will flow, okay, to fill the empty space. So you are sending a signal to the CPU. Okay, there is a electricity flowing here, and so that means that person hit the letter B. Isn't that cool? Huh? Very cool. Okay. So there is no unit, and the variable is just the material that you are using. So if you are using air, dielectric is 1. So that equation here, you just replace that by 1. If you are using mica, that's this expensive smaller capacitor, you multiply by 7. It has no unit, okay? There is no unit for that physical quantity. Are you doing it? Yes. Okay, so first you translate 5 times 10 to the negative 3. So D1, you push, now it's going to be D2. The area is not going to change. Okay, you are changing the geometry by changing D, and the dielectric constant is K. So capacitance 1 before you hit the key equals K proportional to the area, inversely proportional to the distance. So K is 3.5 times the area, so 9.5 times 10 to the negative 5, divided by the distance between the plates, and that's 5 times 10 to the negative 3. So before you hit the key, before you change the geometry. And you get... did I forget something? Yes, that's what I forgot. Thank you. I was trying to find what I forgot my epsilon zero here. Thank you. I was thinking I'm missing something. Yeah, so the equation is K epsilon zero area over D. Okay? So make sure you know how to use your TI, and you make sure with your TI you frame. Okay, you doing it? We can help each other. So 0.589 times 10 to the negative 12 farad. Did you get that? No? Yeah? No, 10 to the negative 11. Let's see. Is that or did I make a mistake? So you can say it's 5.89 times 10 to the negative 13. It's the same thing. That will be the same thing as 5.89 times 10 to the negative 13. But because we like pico, so that way we can write this is pico. So did you all get that? Otherwise I do it with the TI. Make sure you get it right. Yeah, I did that. The distance is okay. That's your dielectric. Okay, did you all get that with your calculator? Are you sure? So this one. So that's gonna be 0.589 picofarad. Now you change the distance. By changing the distance, you're gonna change the capacitance, right? So let's find a new one. That's gonna be 3.5. And then the area does not change. And then you have the constant here. And then the distance between them is now 0.150 times 10 to the negative 3. And now what you get? Yes, 1.96 times 10 to the negative 11. Okay. Or in pico, 19.6 times 10 to the negative 12 farad. So that way I can write picofarad. Okay? Is that clear? So make sure you do it right with your TI. You have the answer. So you can, it's good to have the same here. You see the same power of 10, 10 to negative 12 and 10 to negative 12. Okay, otherwise it's hard with a TI. You forget about the 10 to negative 12, and all you have to do is 19.6 minus 0.589, and that's what you get. But you put your scientific notation on the side when you are subtracting. Make sure it's the same scientific notation. So it's like you factor out the power of 10. Okay, you see that? Because otherwise your calculator is going to be confused and you have a lot of decimals and you don't know how to round. So that's why you need to have the same power of 10, move it on the side, and you just subtract those numbers. That's going to be your delta C. Okay, everyone? So we are reviewing math at the same time. So here is by the way, you can you have other equations here. You can find the energy stored in an electric field here between the plate of a capacitor, and remember that will be the electric field, voltage over distance. Is that clear? So you see here, we have like a new equation. So sometimes in your book, I don't know which book you are using, but hopefully the Johnson and Cotnell, this here, you can call that epsilon. So in that case, epsilon is the permittivity of the substance. It doesn't really matter. What matters is that K, the dielectric constant, has no unit. Dielectric constant has no unit. Okay? You subtract. And when you subtract, you want to make sure that you leave the scientific notation, you leave the power of 10 on the side, because otherwise it's hard. You don't want to have a 10 to negative 13 here and a 10 to negative 12. Otherwise, it's going to be confusing. You want to make sure to have the same power of 10, and you just do 19.6 minus 0.589, and then you bring back the scientific notation. Okay? So it's a review for scientific notations. Is that clear? Okay. Okay, let's do some problem so you can help each other, talk to each other, blah blah blah. Uh, you have all the equation. You have all the equation that you need here. So you have this equation, you have this equation, you have that equation, or you can use this equation as well. All these are for parallel plate capacitors. That will be the energy store. So electric field inside the capacitor. Then here you have the definition of the capacitance. Here you have the capacitance of a parallel plate capacitor. The electric field coming from there inside the capacitor, the energy stored inside the capacitor. That's why I'm telling you, you need to have your equation sheet next to you. Okay, go. Let's do the first one. Do. Help each other, talk to each other.
I don't know how to make it. When I put the equation with the parentheses, this is what I get for the second. So it's slightly off.
For the second one? No, that's the same thing. 1.96 times 10 to the negative 11 is the same thing as 19.6 and 10 to the negative 12.
It's the same.
It's the same. It's just that if you want to have 10 to the negative 12 here, you divide by 10 here. So you multiply by 10 there. Like if you want to convert that in picofarad, okay, so 10 to the negative 12 is pico, right? So divide by pico. So it means 10. How do you do 10 to the negative 12? Okay. 10 to the negative 12.
Wait, the print.
Fix that. Okay. Oh, there is. Okay. So you get 1.96 times 10, which is 19.6.
Okay.
Okay. So then you have to go back to normal.
Well, I've been in scientific. So I try the.
Okay, try again without scientific notation. But it's the same thing.
Okay. I just don't want to confuse myself during the exam. Is this going to be on this exam? Or...
Yeah.
Okay. I need to the. I'll make it a different.
Keep going, right?
It still comes out that way for me.
Okay, so you divide by, which is the same thing. This number is the same thing as here. So divide by 10 to negative 12.
I have a similar question.
You divide by 10 to the 12 instead
negative
of
12.
negative 12. So can you go back? Okay, it's going to give you the same thing. But this answer is correct.
Okay.
It's just that you see it's 10 to negative 11. So you multiply by 10 on one side, which is 19.6. So you divide by 10 on the other side. So if you divide by 10 scientific notation, it's like 10 to the minus 1.
Okay.
So it'll be the same thing.
The answers for Farad are always going to be in pico.
But usually, sometimes they give the answer in pico. So in that case, it will be 19.6 picofarad.
Well, then I'll just do 12 and move it over one.
I don't understand why. Yes, you can. So I don't understand why you cannot divide that by 10 to negative 12.
I don't understand it either.
So 10 to the minus 12.
You do that at the end, like after.
Okay. 10.6 times 10 to negative 20. You see?
Thank you.
Question. I'm trying to solve it. I have like all this written down.
Yeah.
I'm just trying to solve at least one of them.
So this is correct. 5.88 times 10 to negative 13.
Oh.
It's the same thing as that. You see? If
You went
here,
push up.
so if here you multiply by 10, so here you divide by 10. So if you divide by, let's say you want to put in pico, so divide by 10 to negative 12. See what you get. Divide by 10 to negative 12.
Like a question?
Yeah. So 0.589 times 10 to negative 12. You see how many goes, how many pico you have? 0.589. Right?
All right.
It's the same thing.
Same thing.
So it's just scientific. So if you have a scientific notation, if here we divide by 10, that will be 10 to negative 13. So here you multiply by 10, which is 5.89. Right?
All right. Got it.
Yeah.
What is the electric field between the plates?
Yeah.
How do we do that if we, for instance, warn that?
Oh, maybe I didn't give you the distance. I didn't give you the distance between the plates, so you can skip that. Okay.
Correct. And then do that. I did it in minutes.
So here you are missing. So here you cannot. Here you can not find the electric field because you are missing the distance between the plates. Okay, so we have capacitance is 180 microfarad. So you convert that in scientific notation. Okay, and the voltage is 120 volt. What is the charge? Okay, capacitance or Q is CV, right? Curriculum vitae. So Q equals C 180 10 to the negative 6 times 120. So what you get? 0.22. So 22. That's it? So yeah, but I'm rounding 0.216, so 0.22 watts. That's it? Yeah. 0.0, thank you, 22 coulomb. And if I want to convert that to millicoulomb, since we are in scientific notation, you multiply by 1,000, that's going to be 22 millicoulomb. So 1 milli is 10 to the negative 3. So if you have 0.022, how much is that in milli? So you divide by 10 to negative 3. Okay, how much energy? So the energy, I should not put E because it's not the electric field. So energy equals 0.5 C V square. Okay, you look at your equation sheet here. The amount of energy stored inside an electric field, you can either do 1/2 QV or 1/2 CV square. Okay? Do you agree? So the energy stored inside the capacitor will be 0.5. You put parentheses with your TI, so C equals 180 times 10 to the negative 6. Another parenthesis, that will be 120. And you get 1.08. So about what? 1 joule. Did you get 1.08?
Oh wait, I didn't.
Oh, I know. It's a square. Yeah, 1.296. So the 1.3 joule. Okay, I forgot the square. There's a square here. Here, the energy inside the capacitor. Okay, you can go back to here. Energy inside the capacitor is 1/2 capacitance V square. Capacitor energy stored inside an electric field. Electric field is a energy storage. I think we did that already. Okay. What about this one? This one seems easy. So this one is easy, right? So Q equals curriculum vitae. Okay. 8. Pico stands for what? 10 to the negative 12. Very good. And voltage is 5.5. Q equals in scientific notation. Very good. And to make sure you know how to deal with scientific notation, convert that in pico. In pico. So it means you divide by 10 to the negative 12. Pico. It's going to be 44 picocoulomb. Or you can say, if you divide by 10 here, you multiply by 10. So multiply by 10 is 44 divided by 10. Each time you divide by 10, your scientific notation increase by 1, except there is a minus. So if you divide this by 10, it's going to be 10 to the negative 12. Again by 10, 10 to the negative 13. If you multiply by 10, it's the opposite. Multiply by 10, 10 to the negative 10. Okay, so just a review of scientific notation. Okay. We are just reviewing scientific notation. Isn't that cool? Here. Okay, it's useful for chemistry, biology. You have to deal a lot with micro and pico. So calculate the voltage, question mark. So that will be your capacitance, and that will be your charge. Okay. So capacitance is the charge per unit voltage. So you are finding, so delta V equals Q over C. Because you cross multiply, divide. So here, look, you don't have to deal with scientific notation because 10 to the negative 12 micro, sorry. I was checking if you you see what's going on here? So you don't have to deal with we don't have to deal with scientific notation because they cross out, and you see you can do it in your head. 2 goes into 3 about I mean 3 divided by 2 is 1.5 about. Okay, so 1.55 volt. Okay, it's good for your biology, all those 10 to the negative something. Let's do the Van Graaff generator. No, we did that already. Okay, let's do this one. This one. Okay, so that's a micro. That's your delta V. That's going to be Q. So capacitance is the charge per unit voltage. Okay? So make sure you do it and you get, yeah, 2.5 times 10 to the negative 8. Negative 8? Okay, I'm wrong. 2.5 times 10 to the negative 8. So if you divide by 10 to the negative 6 to get micro, what do you get? Uh, so 2.5 times 10 to the negative 8 divided by 10 to the negative 6 to get micro. Very good, very good. Micro. Or you can say you can do this from here to there. You divide by 10 to negative 6 and you get micro. How many 10 to negative 6 goes into? Okay, I didn't lose anyone. Someone is on the phone. I see. Don't be on the phone, okay? Do the problem. You have less work to do at home. Million. 10 to the 6, mega. Ah, isn't that nice? We review all those power of 10. So capacitance question mark, that stands for milli. This is milli. So 10 to the negative 3. And the voltage, that's mega volt. Mega is 10 to the 6. It's a million. Okay, that's 1 million, like a megabyte, a million. Mega, exactly. 10 to the 6 volt. So, capacitor, it's Q. 6.6, yes, 10 to negative 10. Okay, so with your TI, 8 e to the minus 3, close the parenthesis, enter, divided by. All right? Yes? 6.7 times 10 to the negative 10 farad. Did you get that? Make sure you frame the denominator. Right? Do you get that? So with your TI, you do 8e minus 3. Okay? Mega. I'm going to lose my voice. Okay, do you all agree now? Yes? About that. Okay, what else can we do? Teflon. Okay, let's do this one. Teflon you go back a few slides to find the dielectric constant of Teflon. Okay, so this is the area. You see, first thing you translate, right? Physical quantity is a distance, 0.1. Milli, you look at your equation sheet, is 10 to negative 3. Teflon, you have to go back, and let's look at Teflon somewhere. 2.1. Where is it? Teflon, 2.1. Dielectric constant, okay, it's gonna enhance the capacitance. So kappa, it's not a K, it's actually a kappa. It's like a Greek letter. I don't know how to do it. So kappa. So the equation, capacitance equals, you see, I have your equations here. K epsilon 0 area over distance. So it's going to be 2.1, 8.85 times 10 to the negative 12. The area is 5. And then the distance is 0.1 times 10 to the negative 3. Kappa. It's like a Greek letter. Now, it's a kappa. You see, you have delta, kappa, lambda, blah, blah, blah. Okay, what you get? I didn't do it, so I'm going to rely on you. What did you get? 9.29 times 10 to the negative 7. What's the unit? Farad. Farad. Right? Did you all get that? So if you want to go in micro, let's do micro. What do you get? So you multiply by 10. So you divide by 10. So it's going to be 0.2. 9 times 10 to the negative 6. So that's going to be 0.929 microfarad. Okay? Yeah. Here you have to convert, right? So 1 millimeter is 10 to the negative 3 meters. So 1 meter is 1,000 millimeter. It's a lower k. It's a lowercase k, kappa. It's a Greek letter. You know, sororities, fraternities, they call the kappa, gamma, whatever. Okay, any question? So make sure you go over your equation sheet, okay? So you know how to decode all those equations. Let's see. Okay, so charging, discharging. So that's going to be on the test up to here. Starting from now, it's not on the test. but I just want to go over it quickly. You can charge a capacitor and you can discharge a capacitor. So for example, with a defibrillator, you're going to discharge it in the heart. So when you are charging a capacitor, let me ask you something. Imagine you have this reservoir, okay? And to put water into the reservoir, you have to use a pump. Okay, so you are pushing the water in the reservoir. So you are using energy, okay? That energy is going to turn into potential energy. If you go to New York City, for example, you have those ugly reservoirs on top of building because that's why you have enough pressure for all the ugly apartments that they have, right? So let me ask you something. At the beginning, is it easy to push water to work against gravity? Yes, it's easy because you don't have any water to resist, right? As time passes by, what's going to happen? It's going to be harder because the weight inside is going to increase. So you have to do work. It's going to be so hard. And then even more work. Right? So it gets harder and harder and harder. So when you are charging a capacitor, it works the same way. So here you have the charge, which is like the voltage across a capacitor. So charge is proportional to voltage. So here you have the charge inside the capacitor, and here you have the time. At the beginning, it's easy. And as the time passes by, it gets harder and harder and harder, and it takes a long time to charge your capacitor. So it's not that it takes a long time, it's going to depend on two things. You can play with the time, how long it's going to take to charge a capacitor. What do you think it depends on? When you are charging a capacitor, so you have the power supply, you have the power supply, capacitor, and your load or resistance. So it depends on what. So the voltage, it's going to be your force, right? But for a given voltage, for a given pump, it's going to depend on what? So the time depends on what? The size. It depends on the size. Yes. Okay, so if you have a big reservoir, of course it's going to take more time. Does it make sense? And the size is the geometry. And the geometry is defined by what? The surface area. So the surface area and distance. And how we call that? The capacitance. The capacitance. So it depends on the capacitance. How fast you're going to charge your capacitor, of course, depends on the geometry, right? So it depends on the capacitance. What else is going to depend on? You see, you have a pipe here. If you have a small pipe versus a large pipe, which one will take more time to fill if you have a reservoir here? The small pipe or the large pipe? Small pipe will take more time. So if you build the analogy with a electric circuit, how do we change the pipes? We change like in a circuit, how do you decrease the amount of current flowing in a circuit? The resistance, very good. Okay, so the time it takes to fill a capacitor depends on two things: the capacitance, the geometry. Do you have a small reservoir to fill or big reservoir to fill? And it depends on the resistance, how fast the water or the charge are going to flow. Does it make sense? So if you have that for the MCAT, RC is a constant and it's called the time constant. And it's going to be how long it's going to take to fill 60% of your capacitor. Okay, it depends how large, okay, is your reservoir and how fast the water can run or the charge can run because of the resistance. Is that clear? So you see here, why is it easy at first and then hard at last? So you see you have a power supply. Okay, the power supply is doing work, is pushing an electron on that side. So here you have plus, and then you push another electron on that side, and then here plus, plus, and minus. So at the beginning, it doesn't take much effort. But as you build more and more negative charges here, what's going to happen? Do they like each other? Minus, so they're going to repel. Very good. So at first, it's easy to have an electron here. And then the second is not so bad. But as you increase the number of charges, so that will be minus Q, it gets harder and harder and harder. Okay? So you are depleting this plate of negative charge, so it becomes positive charge, and that will become negative charge. That's how you charge a capacitor. Okay? So that's for those who take the MCAT. So if it's in the, but it's interesting to understand the principle. Once you understand the concept, everything else is just math. It's not that hard. And you see, you have a nice equation for that. I'm not going to ask you about that. What about the opposite? Now you want to discharge your capacitor. Are you with me? Let's do a little bit of critical thinking. You have a reservoir, it's full of water. You open the circuit here. Okay, so the water is going to flow. At the beginning, does it go fast or slow? You have all this weight here. Is the weight helping? Yeah. So it's going to go fast. And then it takes forever to empty it because you don't have that much pressure pushing. So capacitor works exactly the same way. If you look at the charge as a function of time, when you are discharging your capacitor across your heart, for example, first it's going to discharge quickly and then it takes forever. And because you are taking biology, all of you, I'm sure you know that function. What is that function? Something going down but very quickly. Start with a E, X, exponential, D, decay, exponential decay, right? Exponential decay. Like radioactive substance, you have a exponential decay. What is the opposite of an exponential decay? Exponential growth. Very good, very good. Okay, you have one rabbit, and then you have two rabbits, and then you have four rabbits, and before you know it, you have 1 million rabbits. They have an issue in Australia with this exponential growth of rabbits. Okay, so I have like the human cell, isn't it? So I have a short video just to show you. I have 1 minute. Do I have 1 minute? Okay, so it's a very short video to show you. So I don't have time, so I'm gonna share the link in announcement. And especially if you go into doing research or whatever, and if you want to understand capacitor, like when you have a model of a cell, you do have capacitors, so it's interesting to understand how they work. So I will share with that. That's not on the test. What is it that you have so much to tell to each other? No, I'm just kidding. It's good to talk to each other. No, it's very good, right? Collaborative learning. It's just because you are in front of me. That's why I'm sorry. No. Collaborative learning is very good. Networking is very good.